Hey, welcome back. In this set of videos, I'm going to talk about applications of the determinant. There's really two key ideas that will be discussed inside this section. The first one is how we can use the determinant to find the solution to a system of linear equations using something called Cramer's rule. So to begin with, this new rule or this new method is only going to work for a subset of systems of linear equations. It's only going to work if the coefficient matrix A is square. So it has to be 2 by 2 or 3 by 3 or 4 by 4. You can't have more equations than unknowns or more unknowns than equations. If you do, then you can't use this new rule. The other requirement is that the determinant cannot be 0. You'll see why in a moment. The method itself looks bizarre, and I'm not going to actually prove it. I'm not going to prove that Cramer's rule works. What you can do is you can look at the examples we're going to use Cramer's rule for and solve them another way. Solve them, for example, by row reduction or solve them by the method of inverses. Before we get to Cramer's rule, I have to talk about a new type of matrix called a replacement matrix. And that replacement matrix will be a matrix that's created by taking one column in a coefficient matrix A and replacing it with the right-hand side of the system of linear equations, the column vector or column matrix B. There'll be a new notation, a new shorthand that we'll use for this matrix. And here it is. So the matrix A of J is the matrix that you get when you start with the matrix A, which is always going to be a coefficient matrix from a system of linear equations, and you replace column number J with the right-hand side of the system of linear equations. You replace column J with the vector B. So let's do a quick example of finding three different replacement matrices, A1, A2, and A3. A1 corresponds to replacing the first column with the right-hand side. A2 corresponds to replacing the second column with the right-hand side, and A3 corresponds to replacing the third column with the right-hand side. So the index, the J index, tells you which column to replace. Tells you which column to replace with B. And I'll identify what B is. And very important, identifying what A is. Step 1, let's extract the coefficient matrix from the system of linear equations. So the coefficient matrix, 1, 1, 1 for the first column, 1, negative 1, 0 for the second column, and then negative 1, 1, negative 2 for the third column. Now we can also extract the right-hand side, B, which is 6, 2, 0. As a column. Okay, and then from these we can construct the replacement matrices from this. So A1 is going to be, and actually I'm going to change my color coding for B, make it a little bit easier to identify what's going on when you're looking at the notes in printed format, for example, or just going through this. Okay, so A1, this is a new matrix that we get by replacing the first column with B, with 620. So 620 goes in the first column, and then column 1 and column 2 are the same as they were originally. 1, negative 1, 0, negative 1, 1, negative 2. We get the same thing for A2. A2 means replace the second column. So I'll leave a space for that. I might as well make A3, leave a space for that one, and then start filling them in. So for A2, the first column stays the way it is. We're not replacing it. We're keeping it as 1, 1, 1. Now the second column gets replaced by 620. And then the third column stays exactly the way it was, negative 1, 1, negative 2. Okay, and then the last one, the first two columns stay the same. So 1, 1, 1, 1, negative 1, 0. And then the last column gets replaced by the right-hand side, 6, 2, 0. Okay, and that's just creating these three new replacement matrices. That's all that we were asked to do. So we're building these so-called replacement matrices in order to use this new Cramer's rule, which I haven't defined yet. Okay, and this just goes visually through, again, the same idea. What are you replacing each vector, or each column with? What we're going to do with these new matrices is we're going to use them to output the solution to a system of linear equations. The variable x sub j, so this might be x1, x2, x3, and x4, or it might be x, y, and z. So each of those xj is going to be given by the determinant of the replacement matrix aj divided by the determinant of A. This is, if we have a quick method or an efficient method for calculating determinants, this is an extremely efficient way to find a solution to a system of linear equations. It's much faster than row reduction. For example, if we have a 3 by 3, to calculate the solution to a system of linear equations, it's 3 by 3, we first check if the determinant is non-zero. Then if we can show that it's not zero, then the x value is going to be given by the determinant of A1 divided by the determinant of A. The y value will be given by the determinant of A2 divided by determinant of A, and then the z value will be given by the determinant of A3 divided by the determinant of A. And we would calculate each of those four determinants using any method you want. The secret method, cofactor expansion, row reduction if you're desperate, so transform to upper triangular or lower triangular form, and then the determinant is just going to be the product along the diagonal. So we use any of those shortcuts, any of those methods to calculate those determinants. So before we proceed, I really want to highlight that this method does not always work. It again does not work if the determinant of A is 0. This formula tells us that we would be dividing by 0. And it also doesn't work if the coefficient matrix isn't square. And this formula also tells us that because a non-square matrix, so a 3 by 4 or 4 by 5 or a 2 by 7, such a matrix does not have a determinant. Only square matrices, only n by n matrices have a determinant. And it definitely does save us work if we use the most efficient method available for calculating the determinant. Okay, and just make it super clear, you cannot default to this method. You have to check these requirements first. If it isn't square, don't bother looking any further. If it is square, don't construct the replacement matrices right away. Check if the determinant is 0. If the determinant is 0, no dice. You cannot use this method. You're going to have to use some other method. You won't be able to use a method of inverses either. Whenever the determinant is 0, the inverse doesn't exist. So you're stuck with row reduction, and you're either going to get no solution or you're going to get a family of solutions for an n by n matrix that has this determinant equals 0. The unique solution only happens if the determinant is non-zero. Okay, so let's use Cramer's rule to find the solution to that system of linear equations that we already calculated the replacement matrices for, but we'll do it again. So we have our coefficient matrix A is given by 1, 1, 1, 1, negative 1, 0, negative 1, 1, 2, negative 1, 1, negative 2 rather. And I'll color code this one, and B is equal to 6, 2, 0. Yes, we already did this. Okay, so Cramer's rule says that x1 is going to be equal to the determinant of A1, not A sub 1, A bracket 1, divided by the determinant of A. So let's go ahead and calculate that. Let's calculate the determinant of A. Actually, I'm going to get the ingredients we need first. get the needed ingredients. And then I'll put the ingredients together on the next slide. So we need the determinant of A. We need the determinant of replacement matrix A1. We need the determinant of replacement matrix A2. And we need the determinant of the replacement matrix A3. So we're going to need to construct each of those replacement matrices and then take each of their determinants. So the first one, let's just find the determinant of A. Determinant of A, I'll use the secret method. 1, 1, 1, 1, negative 1. Well, I gotta write smaller to get them all on the same slide. 1, 1, 1, 1, negative 1, 0, negative 1, 1, negative 2, and then make a copy next to it. Okay, and then our determinant will be down products minus up products. So the first down product, we're going to have 1 times 1, or 1 times negative 1 times negative 2, which is positive 2. Then we'll have 1 times 1 times 1, which is 1. And then we'll have 0 minus the up products. So the first up product we have is 1. Negatives cancel. Second up product we have is 0. And the third one we have is negative 2. Now we can simplify. So that will be 3 minus negative 1, which is 4. So that's our first determinant calculation. We're going to have some more. We're going to need the determinant of the replacement matrix A1 next. So that'll be the determinant of A1 is equal to the determinant of 1, negative 1, 0, negative 1, 1, negative 2, and then replace the first column with 6, 2, 0. So we're going to make 2 copies, put them side by side. So 6, 2, 0, 1, negative 1, 0, negative 1, 1, negative 2, 6, 2, 0, 1, negative 1, 0, negative 1, 1, negative 2. And then we'll have down products minus up products. And hopefully a nice number comes out. So the first down product, we get 12. Second down product, we get 0. And third down product, we get 0. Then now we have the up products. So the first up product is 0. Next up product is 0. And the last one, we have negative 2 times 2 times 1, so negative 4. We have 12, subtract negative 4, which is 16. Now we have to do the other 2 replacement matrices. So the determinant of A2. That'll be the determinant of the replacement matrix where column 1 is the same, 1, 1, 1. Column 2 gets changed and column 3 is the same, 1, 1, negative 2. Okay, so I'm going to put the 6, 2, 0 in the middle this time. Okay, then we're going to make 2 copies. 1, 1, 1, 6, 2, 0, negative 1, 1, negative 2, 1, 1, 1, 6, 2, 0, negative 1, 1, negative 2. And then we have down products minus up products. Okay, so the first down product, we're going to have -4. Second down product, we'll have +6. And the third down product we have is 0. And then the up products, 1 times 2 times -1, so -2. And then 0. And then -12. So we have 2 subtract -14. So 2 plus 14, we have 16. Now we have one more. The determinant of the replacement matrix A3. So row 1 stays the same, row 2 stays the same as the original 1, -1, 0, and then row 3 gets replaced by 6, 2, 0. And we'll make 2 copies, 1, 1, 1, 1, -1, 0, 6, 2, 0, 1, 1, 1, 1, -1, 0, 6, 2, 0, and then do the down products minus the up products. It's very mechanical. Unlike row reduction, where you have to be strategic, except for the selection of the method that you use to calculate the determinant, there isn't much strategy for these. Okay, so the first down product, we'll have 1 times -1 times 0, which is 0. Second down product, 1 times 2 times 1, which is 2. And then the third down product, 6 times 1 times 0, which is 0. Minus the up products, 1 times -1 times 6, which is -6. 0 times 2 times 1, which is 0. And 0 times 1 times 1, which is 0. And we can simplify. So that's going to be 2 plus 6, which is 8. So we've created all the ingredients we need to use Cramer's rule. I'm going to do that in the next slide. Oh, I can't do that in the next slide. Yeah. Do some magic. 1 second. Okay, so the magic's done. I just shrunk the slide to make enough room to do the rest. Now use Cramer's rule. So Cramer's rule says that x1 is equal to the determinant of the replacement matrix A1 divided by the determinant of A. So that will be the determinant of A1, we got 16. Determinant of A, we got 4. So 16 over 4, we're going to get 4 for that. So that's our first answer. Now we're going to get x2. x2 is the determinant of A2 divided by the determinant of A. So that's going to be the determinant of A2. We got 16 as well. So 16 over 4. We also get 4. And now the last one, we have x3 is equal to the determinant of A3 divided by the determinant of A, and we can plug in our numbers. 8 over 4, we get 2, and that's it. How do you check? Well, let's check if row 1 is true from the original system of linear equations. x1 plus x2 minus x3 is equal to 6. So 4 plus 4 minus 2, 8 minus 2 is equal to 6. It worked. and we can check the other rows as well. We'll look at some more examples in the next video.